Can we please have Mr. Siddharth Shenoy?
Uh,
Okay, over to you, Mr. Siddharth.
yeah, I'll just share my screen.
Yes, please.
Yeah. So is my screen visible?
Yes.
Okay. All right. So good morning, everyone. So today my team and I are going to present a solution to a problem that majority of ML projects face and how to sustain a ML product. So at the end of this presentation, we'll know what is ML observability, what can go wrong, what what observability helps in, and what are the solutions to this problem. So the development process of a software system with a machine learning component is more complex than traditional software because we need to monitor variations in three different aspects. That is the code, the model, and the data. As you know that more and more teams and companies are trying to incorporate machine learning into their product, they are trying to find more tools and people to make their idea from research phase into production phase. So let's start the presentation with an example. So more than 50 years ago, the Apollo 11 mission made humans land on the moon. The code that allowed the engineers to monitor the spacecraft's performance and make accurate real-time decisions was a small code base that allowed the engineers to debug it manually. In the age of distributed computing, there are complex applications with billions of lines of code, and also there are plenty more components that need to be monitored, and all this cannot be done manually. The observability is a proactive approach that makes modern IT systems reliable and high performing. It helps you to measure a system's internal states by examining its output, such as logs, metrics, and states and traces. Many top companies like Google, Uber, etc., make incorporating machine learning into their product look extremely easy. But the reality is that the POC of machine learning product during the research phase is very different from making a machine learning model that works in real world. So if something breaks in your environment and you don't know how it happened, it compromises the integrity of your product. But even worse, it compromises the trust of your stakeholders. So let's come to present. The model's ready. What could possibly go wrong? The problem can be arranged in three big groups. Them being bug detection. This is hard due to feedback delays. It is well known that the data distribution changes or shifts over time. This causes the model's performance to drop, and detecting this performance drop post deployment is challenging due to lack of ground truth data. This happens because the feedback on the predictions arrive at much later time. End-to-end machine learning frameworks such as TFX and SageMaker monitor the internal pipeline state or the health via distance matrix, but these proxies often produce false positive. And it brings us back to the point that bug detection is really hard. Uh, there is a saying in there's a well-known saying in production level ML pipelines that changing anything changes everything, and this change causes predictions to vary unpredictably. So this means that even if a failure is confidently detected, the complex and highly intertwined nature of the components of ML pipeline make it hard to understand where the bugs could actually lie. So even if the engineer is able to detect the bug, is able to diagnose the bug, but there are so many different components in a in a machine learning model that fixing a particular problem has many solutions. For example, different components, when fixed, can cause different magnitudes of improvement in ML performance. Users often have no sense of what to fix first relative to the cost in resources and in time. So now the ML pipeline is established, but the work does not end at establishment. ML pipelines must be maintained, debugged, and improved. So how does MLOps or DevOps or observability actually help us in this problem? improve and iterate. So, ML observability is a tool used to monitor, troubleshoot, and explain machine learning models as they move from research to production phase. We want the tool that should not only automatically display the surface level issues, but dig deeper and drill down to the root cause of the problem. If it is a supervised learning model, tracking the frequency of the labeled data over a time period is useful. More labeled information can be observed over time. After a significant amount of new labeled data, it might be best to retrain the model. It enables fast actionable performance information of the models deployed in production. Common metrics include accuracy, recall, F1, MAE, and precision. Performance analysis in ML observability system ensures that the performance has not degraded drastically from when it was trained and tested to when it is initially promoted to production. ML observability encompasses drift to monitor from a change in distribution over time, measured for the model's inputs, outputs, and actuals of the model. Detecting drift in your model will help protect your model from performance degradation and allow you to better understand how to begin the resolution. ML observability can be used for tracking the distribution of each of the features which is necessary to train the model. Also, track the distribution of each of these features necessary to generate a prediction with the model. Uh, Data quality checks in ML observability system identifies hard failures within the data pipeline between the training and production that can negatively impact the model's performance. Data quality includes monitoring for cardinality shifts, missing data, and more to better gauge the model's performance issues. The targeted distribution tracks the distribution on the target label on which the model was being trained and also tracks the distribution of the target label being predicted in production. So, what do we mean by interpretability? We mean that we want to have a qualitative understanding of the relation between the prediction of the model and the components of the data instance that the model used to generate these predictions. These components can be the features of the data instance, or a set of pixels in the image, or a word in a text document. We want to see how the presence or the absence of these components actually affect the prediction of the model. It is usually achieved by calculating the matrix such as SHAP, that is sharp, and lime, to continuously improve machine learning models. So, SHAP, so what is SHAP? SHAP. SHAP is a mathematical method to explain the predictions of the machine learning model. It is based on the concept of game theory and can also be explained by predictions of any machine learning model by calculating the contribution of each feature in the prediction. So, what is a solution to all these issues? Our solution can be split into three main parts. The first being a centralized dashboard. So, this part comes into the execution layer of our idea. The execution layer wraps around the component. It would be able to run trigger computations such as importance weighting, executing, and fine-tuning the data quality constraints. It would detect drift in the data and time-based anomaly detections. So the advantages of this layer would be that this layer would help in auto storing the logs. The engineer doesn't have to manually look into the machine and update the logs to the server. It would detect the early signs of catastrophic failures, and the data drift, that is the killer of most of the ML models, can be detected at early stages, and the model can be retrained with the new data. Graphical representation. The data observability enables active learning by providing granular, in context information about your data. For example, when an engineer wants to compare different features of the model, that is the accuracy, the F1 score, or the mean, they don't have to go inside the logs and get the data, but they can go directly to one particular dashboard, select the feature, select the model, and observe and get all the data of the model at one point. So the uh, So the advantages would be that the user needs interfaces to assess the label delays, inspect data shifts and constraints, and react across all platforms. It would provide a bird's eye view of the entire ecosystem. This solution benefits hugely from having centralized, customizable analytic dashboard that collates and analyzes the transactions in real time, ensures that we respond to the customers in a timely manner while spotting the errors and latency at a glance. Auto generation of YAML files and container images. So our dashboard also has a part which consists of YAML files, which will have all the required libraries with proper versions of the models to work. At the same time, we would also have a container image, and these images are reusable assets. That is, they are deployable on any host. The developer can take the static image layer from one project and use them in another. This would save them time as they do not have to set up anything from scratch. Our solution indexes and correlates information in the container that makes it researchable and makes it possible to generate alerts and reports and visualizations. So this is a proposed architecture. Let's say that there are multiple ML models which have multiple features. So now if an engineer wants to see the logs or wants to see a status of a particular feature in a particular ML model, they can directly go to our centralized dashboard. They can select the particular feature and the model, and in the drop down, and the entire model's history will be available on the centralized dashboard. Now, let's say that the engineer finds an anomaly. He wants to replicate the entire ecosystem of the model into his local container or his local machine. Here comes the auto-generated YAML file. He can use the auto-generated YAML file and replicate the entire environment of the machine learning model, and can run the machine learning and run the model on his local system. Then comes graphical representation. So when the engineer selects the drop down, there would be an entire graphical representation for the model, which would show the entire history of the model. So now the engineer can look at these graphical representations and note down the early signs of failures. Once he gets to know the early signs of failures, he can change the parameters, or let's say retrain the model, and then see how the future progression of the model goes on. So what is our conclusion? We mainly want to narrow down the cause of the problem. The observability compares distribution changes between a baseline distribution and current distribution. The model owners can do a targeted upsampling when there is a drift. The easy replication of ML environment decreases the setup time and increases the productivity. All of this helps to produce a sustainable ML model in long run, and also increases our confidence in the ML models that have already been in production. Thank you. I would like to thank all my entire team, and I think we are open